looking at another episode in the circle theory. This episode, we're looking at two things. One, angles in the same segment of a circle. That's one. And two, we'll be looking at when a radius meet a tangent. So stay tuned and relax. I will be right back. And we intend to look at the angles in the same segment, right? So we know a segment is when you have a chord, all right, like a chord cut the circle and it divides itself, divide the circle into two pieces. We call them segments. So let us look on a case where we have angle. All right. So here we have an idea where we're seeing that if we should imagine that this is a chord. So let me put the chord here so that we could see the segment of the circle. All right, so let me take this line segment and let me put it from right here all the way across the right here. So we're looking at a segmented circle where we can see that this chord from C to B or BC would have divided the entire circle into two pieces. We call these segment, the region bounded between a chord and an arc, all right? So we have the minor segment down here, and over this side where the diagrams are, we have the major segment, right? So what we're looking at here is that the theory that says angles in the same segment are equal, providing they are standing on the endpoint of a chord. Again, angles in the same segment, angles at D and E, they are equal, providing that they both are standing on the endpoints of the same chord to the circle. All right, for example, BC, all right, they are standing on BC. So the angle at E, we could say BED. You could see that angle at E is going to equal to the angle BDC because both angles were developed from the endpoints of B here and D here. So let us just put on the values so that you could see what's going on. Off. All right, so what we're looking on here is angles in the same segment. They're actually in the major segment of the circle. So let me put on the labels for them then. Let's see. So we have an angle CDB, that is 73.88. You're looking at it right here, right? 73.88. I think I could show you too. Here it is. Angle CDD right here, 73.88 right there. Let me pull this across. All right. And let me mark another angle here, which is C E D. 73.88. So this is the theory. We're saying that angle in the same segment will be equal. So it means then even if I would, even if I would pull this, you could see that it doesn't matter how far I would pull it, it remains 73.88. All right, and this one here, it doesn't matter where I put it, as long as I'm in that segment that starts from B going around here all the way to C around that direction. 73.88 coming around. So as many as we could find, it's going to be the same. And I could say to you, if I put some other polygons on this other side, because in here there will be another segment. So let me just all right. Now, even when I'm shifting, so if I'm shifting the chord, so I'm changing the segment, like I'm making the segment smaller, all right? So I'm changing the chord. We're seeing where these are actually changing, but they are equal, all right? They are the same. Watch me move this around. They are the same. They are the same. And that is what we really want to appreciate, right? So let me put some other ones in the other segment. So I'm putting them in the other segment. As you could see here, I just decorated this other segment, the smaller segment right here. All right. So right now, based on where I stopped these, we're seeing 69.05, 69.05. D and E are the same. Now we're going to be focusing on the angle at K. All right. So if I make this angle, so I'm going to create these angle here. So angle B, K, C. That's 110.95. And definitely, if I go angle B, L, C, I'm get the same 110.95. So if I move this in that segment, the 110.95 remains. And this is how you know it is true. I could overlap this so you're only looking at one angle. Watch me. At a certain point, they become twin. Because okay, so this is the one. This is the one now with the tangent meeting a radius. So you could see here is my radius FJ. That's my radius here at FJ, and the point of tangency or the point of contact is right at J here. You could see it right here. LH or LJH, you could look at it. Let me take off this label there. And let me take off this label here. 1 second, let me take off that label. All right, so I'm saying that the point of contact is J. So we have a HJL, which is the tangent line. And the tangent really passes the circle at one point. So if I could zoom this up for you, you're going to see that it did not cut through. So I'm zooming it up so you could look for yourself. It just touches the circle at J. So I could go back down so that you could see what's going on. So this is what we're dealing with, right? So the tangent touches the circle at the point of contact, and that is where the radius touches that tangent. So if I mark this angle here, right? So I'm going to mark this angle here. All right, I'm marking the angle FJH, and I get 90 degrees here. And that's the thing that we're saying, that when a tangent meets a radius of a circle, we will get a 90-degree angle. All right, so you could see the radius meeting the tangent, the point of contact J, and that is what we're saying. I trust that you understand and that you learn, and I hope you're looking forward for episode 3 when we will be looking at more theories in the circle theory. Thank you for watching.